Testing, testing, testing. All right. So as you know, there's a test. Is it ready 20? Think it ready 20? No. You have 10 cookies? Shouldn't I get like 20 for 10 bulk discount? So you were introduced to the internal forces lecture yesterday. Any comments on this notion of internal forces? Finding the shear and bending moment, yeah. How do you find what? How do you determine where to put the line, the section, how to break it? Well, because the problem will say find the shear and bending moment at point B. And you look at point B on the diagram, that's where you're going to cut it. Yeah. What do you mean by the line of action? What made you think of the line of action? You were doing homework of this one? Oh, chapter 5? Well, you have to show me that. I'm not sure what line of action is. Well, when you're doing moments, you can do the moment. That may be referring to the line of action of a force. And so when you're trying to do the moment about, some point P, and you have a force applied here, maybe going, in this direction. That line of action, which my pen just graciously created for me right there, is anywhere. You can do the moment calculation. You can do the moment calculation at any position along the line of action of the force, and get the same moment. So that's usually what they mean by line of action. The line of action of the force extends in either direction to infinity in the arrow that it's pointing. So if there's a more convenient place along that line of action, or we happen to know a point along the line of action, then you can choose that point. But if you see something that you have a question, bookmark that for me, the problem number. You can maybe email that to me, and I can maybe talk to you about it later, but just so we have a reference that we can kind of, see the specifics of. So yeah, we did all this stuff, and we talked about the the weirdness of the sign conventions with these things. The sign conventions are, of course, the shear force is positive; it's bending clockwise, rotating. If the section is rotating clockwise, that's considered a positive moment. Bending moment's considered positive if it turns the section into a U shape or a smile. And you can decide to do the analysis on either section, and you'll get the same result. And we just did the internal forces at a single point yesterday, but that's really not very helpful when you're working on a real system. You need to know what it is along the whole axis of the beam. So that's what we're going to do today. We're going to learn how to do a shear diagram. We're going to make a graph of the shear versus the position along the beam, and the bending moment diagram. And probably the most intuitive way to do it, since we learned how to cut a beam at different points, you can cut a beam at different x values. And so what you can do is make a an imaginary cut, but instead of calling this cut at some position, like 3/5 L, you can just call this position X, where X is the distance from the left side of the beam. And when you make the cut at that position X, then the variable X will come into the formulas that you're creating, and you'll end up getting a function of X in your answer. So you'll then be able to plot that function of X, which most people are terrible at doing, by the way. So you're going to have to learn how to plot a function again. I know. You thought you didn't need to know all that stuff, but you do. So here's how it works, and then we'll do an example in a second. So I'm just going to kind of go over it with you, and then we'll do this. So here's the problem we're trying to solve, and we already figured out the reactions were 1/3 F and 2/3 F. This is the same problem we looked at beginning of class yesterday. But instead of looking at a certain point, we're going to basically consider this point X. Now, X could be ranging anywhere up until you get to a change in circumstances, like in the beam that you're looking at. So for instance, if you start with X here, X can, when X is 0, there's this force right here, which is a singularity. It's an infinitesimally small, like a delta function force. A delta functions yet, I don't know if that's I think like a differential equations thing you get. Anyway, it's an impulse. It's a very narrow point force. But then beyond that point, like starting here, you have essentially a region where nothing new happens. It's just the value of X could vary. So we can make a diagram for that particular region. In particular, we'll call the 0 less than X less than 2/3 L. Why 2/3 L? What's happening at 2/3 L? There's another force there. And so that changes things. If we were going to go extend beyond 2/3 L, we'd have to include that force in the diagram. But until we get to that point, we just have pretty much a blank beam there with just a force at the left side. So that is one region of analysis. And in that region, we label the free body diagram with a V and an M. And we do the sum of the x's, some of the fx's and some of the fy's and all that stuff. There's no normal force, it's all vertical. So this is the region that we're doing the analysis on. And in this region, we say the sum of the fy's equals 0. Tells us that we have, very simply, 1/3 f minus v. Therefore, v, which is now a function of x, I'm not sure how to actually, this doesn't mean v times x, it means v is a function of x now, right? Is going to equal 1/3 f. It's constant, in other words. It doesn't change. It's a function of x, but it's constant. It's going to change in a second when we get that other force in play. And the sum of the moments, say, at A is going to equal 0, which means I got to get Windows 20, I'm going to get Office 2013 still, which is going to equal M, which is counterclockwise, positive, right? And another moment about A. Who else is going to, what's another moment about A? Jose? One-third F times X, positive or negative? Good. I would say initially, let's just call that minus V times X and put a dot in there indicating it's times. V times X, V is 1/3 F. And yeah, because you've got that V force, right? That's going to cause a clockwise rotation, which that's a negative moment. So put a minus sign there. And so therefore, M is going to equal V, which is 1/3 F times X. So 1/3 F times X. Meaning, as you get farther away from the left side, the bending moment gets bigger, doesn't it? It's growing linearly as a function of X. This is also M of X. And I don't know if I'm always going to put that in there or not, but this is to clarify that these, from now on, are going to be functions of X. In this range, the formulas we just determined only apply to this range from 0 to 2/3 L. Exclusive. You go outside that range, the formulas don't apply. But there is an interesting boundary condition in that the bending moment is not going to be able to change instantly. We'll talk about why that is later. But you can actually think about, well, what's going to happen at X equals 2/3 L with the formula that you just came up with. And at that point, that's the point where the new force comes into play. Just using the old formula, the bending moment, M of 2/3 L equals 2/9 FL. That becomes a checkpoint, because when you look at the next region, you come up with a second formula, the bending moment has to be the same at that point from one region to the other, because you can't have a jump in the bending moment. Okay, so that's basic idea. Then we look at the next section. So now suppose you allow X to go further. We allow it to go past 2/3 L. So now X is in this region here. X is going to sort of be continuing. This is the range we're looking at, and this is the region in which 2/3 L is less than X is less than L. So this will go all the way to the end of the beam. Right. So this is the region here. Right. So this is the first region, and this is the second region. And you could even put, region 1, region 2, if you want to kind of be clear about what you're doing, right? These are the domains of X now. It's region 1. And now we're going to do region 2. Very helpful thing. Question?
So on the other previous things, what does those numbers mean? Specifically the 2 over 9 FL?
What do those numbers mean, the 2 over 9 FL? Well, what is F? F is a force. And what is L? L is a length. It's a moment. It's a force times a length. Pardon me? Yeah. Oh, M parentheses 2/3 L is the moment at that location, 2/3 L, right here. That's what the moment's going to be right there. But over here, it's going to be something else. Over here, it's going to be something else. It's changing as a straight line. Yeah, because when x equals 2/3, you multiply 1/3 F times 2/3 L, you get 2/9 FL. Isaac? Is V a value that we create, or what does it represent? V is an internal force that material has to deal with when those loads are applied to it. And our job is to figure out what those internal forces are. Is V the result of F on the far right side? Yes. The applied load, it's not on the far, at 2/3 L, that applied load is causing an internal force reaction to take place inside the material of the beam, right? Because if the beam can't withstand that force, it's going to fall apart. If you make your beam out of spaghetti, it's not going to handle that, right? Make it out of cardboard, it isn't going to be strong enough. It can't withstand that force. So you have to determine these forces so that when you design your building or whatever, once you figure out what the forces are, you choose the material and the beam so that it can withstand those forces. That's the missing piece of what we sort of have been doing so far. In the bridge design, if you're going to do that extra credit, there's some tables of what are the maximum tension and compressive loads for the balsa wood that you can use. Because it's a truss, the forces are very simple. They're either tension or compression. You don't have to worry about bending moments or shear forces. Because there are only 2 force members, the forces are all going to be normal forces only. But with other structures like frames, you have these various forces going on. Yeah, in this style of problem, our job is to find those internal forces. No, we're just starting region 2 right now. And our job is we want to find it throughout the whole beam. There's no point in just determining at one point if it turns out to be bigger at another point, right? We want to know what the whole beam is doing. So we know that that beam is actually capable of handling a force. Yeah, that's why we're doing this. So in region 2, we do the equations all over again. This is a very redundant kind of process. The sum of the Fy's equals 0. And in this case, we've got our 1/3 F on the left. We've got a minus F going down, right at that point there. And we've got, oops, we didn't label our forces. We've still got our V here and our M here in the same direction because we're looking at a left side section. So we then subtract V as well, because that's pointing down as well, right? So therefore, in this domain, our V of X is going to equal 1/3 F minus F. It's going to be minus 2/3 F. Oops. I say oops, but it's not my fault. This is the fault of bad software. And I have to get a copy of 2013. So V of X, this function of X, is constant, and it's minus 2/3 F. Just by the algebra of the formulas, right? And then we do the sum of the moments. At A again, A is all the way on the left. Sum of the moments at A, what do we got? What's the moment at A? Minus V times what? 2/3? Nope. What's the distance from V to A? X. Minus V times X, right? What's another moment? minus 2/3 L times what? Times F. That's the moment of this force about A, right? Isaac, another moment about A? Plus M, good. And again, that's an M of X. And so we solve for that. Is there anything else? Did I forget anything? No, that looks it. So therefore, M equals V, which is minus 2/3 FL. So it's 2/3 FL. And wait a second. Yeah, minus, oh, it's minus V times X though. So it's minus 2/3 FL. Oops, those are just two symbols. We're multiplying F times L. And it is also minus 2/3, that's the V, minus 2/3 F times X. I switched the order around. And therefore, M equals 2/3 F times L minus X. I have a sign error. This is a plus. Wait, plus 2/3 FL. Is that your question?
So minus B times X and the FL. Substitute the X for the L. And then on the other one, minus 2/3 LF, he substituted X for L. The X and L are not the same thing.
X and L are not the same thing. What is L? L is the length of the beam, and X is a distance along that length of the beam. So X, in this case, has to be between 2/3 L and L. L is the length of the beam. So it's a 20-foot beam, and X is like between 2/3 of 20 feet and 20 feet, right? So X is like between whatever, 16 or something. Isaac? X seems like the length of the section. You should not think of X as the length of this. Well, yeah, it is sort of the length of the section, and it's a number that can vary. That's why we're using a variable X. We can't just use one value for X. We're using a variable so that the X will handle all those different numbers. We plug in, so again, if you think about, let's think of the beam that's like maybe 15 feet long, right? What's 2/3 of 15 is 10, right? So if L is 15 feet, then this applies for when X is between 10 feet and 15. And this other formula above applies for when X is between 0 and 10 feet. L is a constant, it's the length of the beam. F is a constant, it's the applied force. X is changing, it's a variable. Yeah, okay? David. I think I might have an issue here. Let's look at this a little more closely here. So the sum of the moments at A is clearly minus V times X clockwise, minus 2/3 FL, 2/3 L times F, yep, clockwise, plus M. So therefore M equals plus 2/3 LF, right? But it's going to equal plus Vx, but V is minus 2/3 F. So you get minus 2/3 VFX there. Don't you normally not want to worry about signs? No, you have to worry about signs, David. It's just that when you look at the arrow, the direction of the arrow is going to cause a rotation about the, the point of the moment. Okay, now it turns out that V is negative. That means the arrow is actually wrong. It's actually flipped the other way. So that's why there's a sign change, right? Okay, so M equals 2/3 F times L minus X. Now we can do this check again and say, well, what was this formula going to tell us at X equals 2/3 L? And for the bending moment only, they should be the same. So using this formula, our M of 2/3 L. Again, if it's a 15-foot beam, that means that M at 10 feet equals Well, let's see, we're putting in a 2/3 L for x, so L minus 2/3 L is just 1/3 L, right? So you get 1/3 L times 2/3 F, that gives you 2/9 FL. And that checks with what we had up above here, right? See, it's fun, right? Questions? Now, the next thing is, well, what if I don't want to do the left section? What if I want to do the right section? I want you to listen really closely because this is where some people kind of, they kind of go askew here. Okay, because we're going to label this thing. Now we've got to label V going up, right? Because it's causing the rotation. It's going clockwise. That's a positive shear. And which direction is the moment going to be? Clockwise or counterclockwise? To cause a U shape on that beam, that right section. It's going to be clockwise to cause a U shape, right? In other words, we're bending it by doing that to it, and that's causing a U shape on that little section. So that's M. Now, even if you're looking at the right side of the beam, X is still the distance from the left side of the beam. In order for all this to work out, you got to have the same reference point for X, right? So here is the $50,000 question. What is this distance right here? L minus X. Remember, X is the distance to the left side of the beam. The beam has a length of L. You chop it there at some distance X. Think about it. Let's sort of sketch this out here. This is L. This is X. That's still X. It's the distance to the cut from the left side of the beam. So the distance to the right side of the beam is not X. This is where people kind of go astray. Be clear on that, right? This distance here is L minus X. Okay? And that allows this all to work out consistently. If you do it right, you'll get the same answer no matter which side you're looking at. We're still in the domain. This only applies still when 2/3 L is less than X is less than L. Still applies in region. This is just another way of doing region 2. It's an alternate 2, but you're going to have to get the same answer. And we do the sum of the Fy's equals 0. And now, of course, we got 2/3 F acting. That's the support reaction at B. So we're going to have a V going up now plus 2/3 F. So therefore, V equals minus 2/3 F. Doesn't that look familiar? That's the same answer we got just above there, right? And the sum of the moments at B now, that's the right side of the beam, we can do that, equals 0, and that is going to equal, let's do some moments, huh, shall we? Someone give me a moment, Isaac? Minus M, thank you. David? Yeah, or minus V times L minus X, right? Any other moments? Which? 2/3 FB? What? B is a point, not a distance, right? Yeah, that's it, right? That's all there is. And if we massage this a little bit, you're going to find that this means that M also equals 2/3 times F times L minus X. which is the same as the other one, right? Cool. Good. Now we can do, well, now we can actually draw them. Question for them. Yes. Again, it's another way of doing it. Why would you do the right section as opposed to the left section? On what? Yeah, if you have a choice, you can do the left section or the right section. Why would you do the right section? Just like when you do the method of sections on a bridge, you could do the left section or the right section. Why would you do the left section or the right section? Maybe there's fewer forces acting on it. Maybe you get simpler algebra. It's your choice. Okay? Yeah. Regardless, in these two regions, we now have these two sets of equations, and we can plot them. How do you plot them? You plot them by making a table of points, plugging in different values of x until you get the different values at all those different points, and then you kind of sketch where those points are on the line. No, it's not guess and check. It's plugging in values for x, computing what those numbers should be for v and m, right? So you can figure out, okay, so here's x, here's what v is, and here's what m is, right? Well, you can, and there's different, well, so put when x is 0, v is this, 1/3 f, m is this, is 0, right? Because we're just using these formulas, right? You're going to plug in 0 for that formula for v, it's just 1/3 f. What about for m? Well, it's 1/3 f times x, x is 0, okay, so it's just 0 there, right? So the bending moment is 0 at the end, right? Well, what's another interesting point here? Well, what about this this point here at f, where this new force is coming into play? What's the v? Well, the v jumps down to minus 2/3 f, but the m reaches its peak here. If you plug in, well, we already figured out that point, 2/9 f out, right? We determined that point already. And it's a linear function, so we just draw a straight line from there to there, there to there, and we're done. I think 50% of the people are not going to be able to do this on the test. It's really fast. So you should start practicing that. Don't copy the solutions when you do the homework. Try this out and then look at the solution. Yeah. Now we have an example that you can follow along with. Thank you for your patience. This is, we're going to draw the shear and bending moment diagrams for this complicated thing here. This is a cantilever beam. By the way, this is what we had to look at with quiz 4, and a lot of people didn't get that one right either. Cantilever beam has 3 reactions. What are the reactions for a cantilever beam? AX, AY in a moment, right? And so we can just draw this like so. We've got an AY, we've got an AX, which is 0. There's no horizontal forces applied, and a bending moment, which is counterclockwise. This is a counterclockwise bending moment. You can draw it going down that way, or you can draw it going up if you like it. If you like, you can draw it going up this way. This is the same bending moment. And an AY here. Now we want to know what the shear and bending moment is throughout that whole beam, even through that distributed force. So we're going to have to be careful. The trick is how you deal with that distributed force. We kind of touched on that a little bit yesterday. The first part about the distributed load is we got to figure out what is that effective load and where is it applied, right? So the effective load is the area, right? It's going to be a rectangle. It's going to be base times height. So that's going to be 8 times 2. 16. And where's it applied? Well, at the midpoint, right? The midpoint being midpoint. The midpoint being right here at a location of 5 meters away from the left side, right? And so we have this force reduced to 16 kilonewtons, concentrated load, and And we now can figure out what those reactions are, right? We want to find the reactions at A so that we can use those when we do our analysis. So the sum of the moments, or the sum of the forces in Y, boy, it's just getting worse and worse. 2 and 1, that's really good. Means that AY is going to be the sum of those forces. So AY is just 20 kilonewtons. And then the sum of the moments at A I've heard this only happens when you're in projector mode, and maybe I should just do this in non-projector mode. It would be a little smaller, but without all these stupid lines. Why don't we try that? What do you think of this? I think this might work, although it could be its own. Yeah, that's too small, isn't it? Is that too small? Which arrow? Oh, this arrow? But you know what? I think I need to do this to select the pen now. Well, it's blue. I think, let's see, where do I change the pen color though? Well, I think, can I erase? Look, where's the color of the pen? Draw, thank you. Red. And I want it thicker. I'm so glad, everything is just so awesome. Can't figure it out anymore. I want a pen. Okay, good. So now let me hide this. That's not that bad, right? So the sum of the moments at A equals 0, and that equals, you can see that, right? You're all very close. Barely? Okay, wise guy, give me a moment at A. Yeah, minus 4 kilonewtons times 2 meters. What else? Minus 16 times 5. Plus what? M plus M, or actually this is MA, this is a reaction moment at A, let's call it MA, plus MA. So our reaction moment at A must then be the sum of those. MA equals 88 kilonewton meters. What is MA? Isaac, what is MA? It's a moment around A. What's causing that? Where did it come from? The resultant, David says. Is it a resultant? Matthew, is it a resultant? It's what? It's caused by a force acting on a beam. What do we call something that's caused by a force acting on a beam? A reaction. What is the difference between a resultant and a reaction? Explain. Internal versus external. What does that mean? No, I think you're on the right direction, but I don't think you're quite sure what that means. So if I asked you, if I erased all the reactions and I said, what is the resultant of these two forces, the 4 kilonewton and the 16? What is the resultant moment of the 4 kilonewton force and the 16 kilonewton force about point A? You would say it's minus 88 kilonewton meters, right? And that's what some people did for quiz 4. They found the resultant moment. of the forces, but they didn't find the reaction moment. The reaction moment is what's the joint doing to keep that resultant moment from doing what it wants to do. The resultant moment wants this thing to rotate clockwise. What's going to keep it from rotating clockwise? A counter moment going counterclockwise, the reaction moment at the joint. That's the reaction. The reaction plus the resultant has to add up to 0. Yeah, so the reaction has to be plus 88. Has to be counterclockwise. Otherwise, the thing's going to spin like a clock. And it's going to hit somebody on the head. Okay. Yeah, so MA is 88 kilonewton meters. That's the reaction moment at A. Those are reactions, though. Those are actually forces that the beam has to deal with. And so the beam has to be designed accordingly with that in mind. So, so we skip on over to the next slide. And we've conveniently located all the reaction forces on the beam there at A. And we've got our 4 kilonewton force coming down, an 8 kilonewton meter distributed load again, right? And this is where, again, we go into those different regions and we say, okay, region 1 is where 0 is less than x is less than 2 meters. Okay, that's the region that you're seeing right there. We're cutting this beam at x. In other words, it's this region right there. That's going to be region 1. Pardon me? Yeah, question? Is x given to us? This is what's given to you. You're drawing the shear and bending moment diagrams. How are you going to do that? You're going to have to find what the shear and bending moment are as a function of x. It's not given to you. What's given to you is the 4 kilonewton force, the 8 kilonewton per meter distributed load. So you got to say, look at this thing. Look at this region right here between A and B. There's nothing going on there. So let's call that region 1, and we'll make x go from 0 to 2, right? So then we do the sum of the Fy's. Okay. And that equals, well, you got a 20 kilonewton force there. Oops, we got to label our shear force going down and our bending moment going counterclockwise, right? So it's 20 kilonewtons minus V. So then V, which is a function of x, is just going to be 20 kilonewtons throughout that whole region from 0 to 2 meters. Okay. And isn't this interesting, though? I mean, I think it's pretty cool. This is how you probe this thing. You can figure out what these forces are inside a beam. I actually, by the way, I'm doing a project. I'm investigating whether I'm going to do a remodel and take out a wall in my house because it's sort of a stupid wall. It makes a hallway that doesn't really need to be there. And I was talking to Matthew Kyler. You know, he's coming here. He was here last week. He's a structural engineer. I'm going to have him kind of figure out, you know, is it a load-bearing wall, right? So I'm looking inside my attic to see, you know, the struts from the roof coming down. It's a low-pitch roof, and so there's a thing of heat kind of coming down on that wall. Down below, there's these cross pieces. It's pretty awesome. You just get a real, you know, the knowledge that you get from this class is just extremely practical on how this all works. Yeah. Yeah, oh, let's do that tomorrow or the next day. Yeah, remind me tomorrow. Tomorrow's Wednesday. Isaac. I didn't imagine how much force is being applied. Well, if the bridge is going to handle like a car, how heavy is a car? And you put like a load on the bridge of a car. Yeah. And you got to figure out how the weight of the members themselves are going to cause, you know, something too. But anyway, let's finish this problem, then we can have some fun. MA equals 0. The sum of the moments at A has to equal 0 again, right? And so that's going to be, well, we've got our 88 reaction moment applied already at that point, right? And what else is going to give us a moment? Of course, you'll say minus Vx. We've done this already so many times, right? Minus V times X. And what's another moment at A? Plus M. Okay, so that means solving for M, we have minus 88 plus V times X. Well, what's V? V is 20, so it's going to be plus 20X. And let's do our checkpoint at that boundary where X equals 2. What is the moment going to be? When X equals 2, what's that moment supposed to be? Just plugging in an X there in the formula, right? What is it? Minus what? You sure? This is why nobody can do these drawings. Guys, or it's 48, minus 48 kilonewton meters. Is that still legible? Can you see that? It's not as easy to read, right? The pen is too thin, isn't it? I don't think I can zoom in the projector. Oh, maybe I can do the plus thing, but it's then I'm gonna not have the whole screen, but let's see. No, no. But notice there haven't been any of those mistakes anymore. Nope, F11 is gonna project it. All right, we got 4 minutes. We got to finish this thing. Well, what about from, oh man, we're never going to finish. From region 2 now, because unfortunately this has 3 regions. Region 2 is, you know what region 2 is, right? What's region 2? Look at your diagram and tell me what region 2 should be. What's going to be the range for X? Between 2 and 4, right? Oops, that's region 2. As you can see, that's this region right here. So we're going to have X restricted to that region, and then we do the 3-body diagram for that region, and that looks like so. Man, this is really annoying. And in this case, we have a, no, don't touch it, David. You're going to screw it up for the next class. We've got our V, and we got a, I appreciate your engineering. We got a V and an M as well, right? And we just do the sum of the FYs. And that equals, and we got our 20, we got minus a 4, and we got minus a V. And therefore, V equals 16 kilonewtons. And we do the sum of the moments at A again, and wrapping this thing up kind of quickly, it's going to equal 88 minus 4 times 2 minus V times X plus M. So therefore, M is going to equal minus 80 plus 16X. And our check again is that that boundary between region 1 and 2 should be the same. M is going to equal, and if you plug that in, it's going to be minus 80 plus 32. Well, that's also minus 48. Right? Sorry. But now there's another boundary coming up at X equals 4. And let's just do a sanity check there. That is going to be when M equals 4, when X equals 4, that's going to be minus 16 kilonewton meters, or minus 16, yeah, kilonewton meters. We're looking at a left section. We're cutting the beam and looking at the left side. Okay, so the last part in a minute we're going to solve is the final section, which is easier to do. There's just fewer things going on. I'm going to zoom out a little bit. This is a little annoying. if you do the analysis on the right side of that section, you cut this thing, we're still cutting it. We still have a shear, but now the bending moment's going up. Bending moment's going clockwise, and the shear is going up. And this is region 3, which is between, oops, x is going between 4 and 6. Sorry? It's not up, it's going clockwise. Okay, and we know that if you, well, this is actually where it gets kind of interesting, right? Because we're not actually looking at that whole distributed load, we're only looking at a part of it, the part that, is left over when we cut this thing at x. So as we've determined, the beam has a length of 6, so this distance is 6 minus x here, right? And that means the distributed load has a total of what? What's the total area of that rectangle with a base of 6 minus x and a height of 8? Well, it's 8 times 6 minus x, isn't it? It's another function of x. As x gets closer to 6, the area gets closer to 0, right? It gets smaller and smaller. And how far is that thing from, say, D? That distance here is going to be what? Well, if the base of that thing is 6 minus x, why is it 6 minus x, you ask? Because this is x, right? And the length of the beam is what? No, what is the length of the beam? 6. Right? Because we're always referencing x to the left side of the beam. The beam is length 6. So that means that right section has a length of 6 minus x. Okay, right? So how far is it from that load, though, where we simplify the load? What's this distance here? Matthew? Okay, 70, sorry? Nope. What's this distance right here? 6 minus x. David, what's this distance right here? Jose, what's this distance right here? You think he's right? Yes, you don't know. What do you know about the distributed load of a rectangle? Isn't it applied to the midpoint of the rectangle? The rectangle has a base of 6 minus x. What's the midpoint of 6 minus x? 6 minus x over 2. Yeah. 1/2 times 6 minus x, right? So we do the sum of the fy's. And that equals v going up minus 8 times 6 minus x. That's this form going down, right? And notice there's no forces at D. It's just a cantilever. It's just hanging out into space, so it's an interesting beam. And therefore, V is going to equal 48 minus 8x. Some of the moments you can do the moments at x if you want, or at D if you want. But if we do it at x, we're going to say that that equals a minus m. That 8 times 6 minus x force has a moment arm of the other side. That's this moment arm here, but that's also 1/2 times 6 minus x. So we put that here. I'm kind of running out of room, but let me move that down below, I think, and that'll be a little bit easier to read. Do the whole equation down below. It equals minus m minus 8 times 6 minus x times 1/2 times 6 minus x. You can see it starts to get interesting. We're now dealing with polynomials, right? You never thought you'd have to deal with polynomials again, did you? And that means m equals minus 4, and you can even try to clean it up a little bit, times 6 minus x squared, making it easier to plot. So the moment at x equals 4, that's the sanity check we did above, is going to equal, when x equals 4, it's going to be 2 times 2, 6 minus 4 is 2, squared is 4 times 4 minus 4 is minus 16 kilonewton meters, same as region 2. So that checks. And just out of curiosity, the m at x equals 6 is going to be what? 0. Okay, so those are points you can use to draw this thing. And you take these different numbers that you've been developing, and you sketch them. It's not rocket science. You should be able to draw a reasonable sketch, part of your graduation in the pre-engineering program at MPC, of a function of several different parts. And what it looks like is the V is 20. We'll kind of start here, I think, tomorrow, in case this is getting too fast, too late. And the V is going 48 minus 8x, and you can plug in 6 for x and find that V goes to 0 at the end as well. And the M is starting off at minus 88. And it is hitting some points here at x equals 2. It's hitting minus 48. And at x equals 4, it's hitting minus 16, about a third of that. So something like this. And it's sort of linear for region 1. So these are being connected with straight lines. But the last part is actually parabolic. So it kind of makes a parabolic, graceful curve there to the end of the beam. But it's kind of hard to see on that diagram. But if you draw something that kind of looks sort of like that, that's reasonable. It's when you actually draw something that looks like this that I get really upset. The kinds of things I've seen on people's curves are just atrocious. Okay, so we'll pick that up tomorrow, and then I think we'll finish the lecture relatively quickly tomorrow so we can kind of go out, run off, and take a look at the bridge.